Section 7.4, evaluating logarithms and graphing logarithm functions. This is a big, meaty section. We might have to split this thing into two parts, but let's see how far we can get here. So we've been working with exponential functions. We've looked at natural base, exponentials with a base e, and then other bases. And we have had some problems where we've been asked to find or predict the amount of time it takes to get to a certain value given some exponential function. Well, now, with the use of a logarithm, we are able to find the solutions for these powers. When we're looking, for example, a time quantity, how long it took to double an amount of something. Well, now we can use logarithms to do that. And there are different kinds of logarithms. There are common base logarithms. There are natural base logarithms, and we're going to look at all of those. But before we do that, let's just dive into the definition of a logarithm with some base b. So in a logarithm, we have a base value, kind of like we do for an exponential. So we've got this base value here, it's this little subscript number, and then we're taking a log of some value y, and when we do that, we produce this answer of x. So in logarithms, when we work with them, our base values and our values that we're taking the log of, they must be positive numbers. We'll talk about y in just a second. So log base by equal x is how we would say this. And this conversion that we see here going on, it says log base by equal x if and only if. So notation, just a little FYI there. IFF means if and only if. If and only if b to the x is equal to y. So what we want to do here is we want to know this relationship from logarithmic form into exponential form. And we want to be able to go back and forth between them. So I'm going to suggest that when you're working with these problems, you start with writing the generic form, either logarithmic or exponential, with your problem, and then convert to the other form. How do we convert them? Which parts go where? Well, if you'll notice here in the logarithmic form to exponential form, we've already highlighted the fact that you've got a base of a logarithm. Well, that base is the same value as the base of our exponential number. So we say a base is equal to a base. Then we've got the value of the logarithm that we are finding. And in that case, that is equal to what our base raised to a power number is. And then we have the solution to a logarithm, and the solution to a logarithm is the exponent on an exponential form. So if you're thinking of it in a cyclical type of term here, our base raised to a power of x produces a y. There's the relationship. Base raised to a power of x produces a y. All right, so let's use this relationship and see if we can come up with some answers to some of these problems here. There are two logarithms that might be worth noting, logarithm of a 1 and a logarithm that has a base value of b, but also you're taking the log value of that b as well. And in these two special conditions, we can see here, any base value, b, raised to a power of 0, anything raised to a power of 0, produces a 1. And so there's a relationship. When I have a log of 1, I will always produce a 0 answer for that. Here we have a base raised to a power of 1, so b to the first is equal to b, and there's the relationship there. All right, so let's rewrite our forms. How do we go into exponential form from here? So my suggestion is, given a log base 232 equal 5, why don't you go ahead and write directly below this conversion formula. Log base b y equaling x becomes b to the x equals y. And let's identify the components we're working with here. So in this problem, our base is a 2, and y is equivalent to 32, and 5 is equivalent to x. So over here, our base becomes a 2, our x becomes 5, and our y becomes 32. And if I look at that, 2 to the 5th, yeah, that is equal to 32. So there's our conversion from log form into exponential form. So this just gives us some practice on just changing our forms. So again, this is a place where we can pause, try and work B, C, and D out, come back in and check in on the answers. I'm going to go ahead and give you the answers for these right now. 10 to the 0 power equals 1. 9 to the 1st power equals 9. 1/5 to the -2 power equals 25. So in this one, maybe not so obvious. On the first two, it's easy to see, yeah, anything to the 0 power equals 1, and 9 to the 1st equals itself. But 1/5 to the -2 equals 25. Well, remember, that's a negative exponent, which means I can write it as 5 squared, and yeah, that equals 25. 1/5 to the -2 is the same thing as saying 1 over 1/5 to the +2 power, or just make the reciprocal of the fraction and then make it a positive power. So there we are, just rewriting. Good practice, because we're going to be going through that process a lot in logarithmics. All right, evaluating a logarithm, what this means is I want to know what the answer. If I said log base 3 of 81, what does that equal to? We're looking for an answer. So what we'll do is we'll set it up the same, log base b of y equaling x. And we can see our b is a 3, and our x is an x, and our y is a 30, that's an 81. So if I just continue with my practice of converting forms, I see that log base 3 of 81 equaling x is the same thing as me saying 3 to the x equals 81. Now, hopefully, you're going to be familiar enough with your base 3s and 2s and 4s and all your kind of 1 through 9 bases that you'll know that 3 to the 4th power is equal to 81. But what we can do, if we don't remember that, is we go back and we look at the fact that back in chapter 6, we said, if I can make the same bases, when I have two expressions equal to one another, if I can make the bases the same, then I can solve for whatever the variable is, in this case, for this power. And so we can do that. 3 to the x. 81 is 3 to the 4th. So now that my bases are the same, that must be that x is equal to 4. So the evaluation process for log base 381, we get 4 for that. So we're gonna kind of continue with that theme when we're doing this. We want to try and make bases all the same. If we go ahead and do our change from logarithmic form into exponential form for this one, we got 1/4 base to a power of x is equal to 256. And then, now I've got a base that's fractional, and then a 256. And when I have a fraction where the numerator is 1, remember that what that means. Right now it means 1 over 4 to the 1st. This is the same thing as writing it as a negative exponent. So 4 to the -1 power to the x equals 256. Well, now if I can make that 256 become a base 4 number, and it is, 4 to the 4th power is equal to 256. So now I can write this as 4 to the power powers makes this negative x equals 4 to the 4th. And then I get from that negative x is equal to 4, so x must equal -4. So this whole thing just equals -4. So when I start with a logarithmic base that's a fraction, I'm always going to get a negative solution of that. And again, you should be, if you want to practice these, you can be pausing and checking in. Now, we haven't seen anything like this. There's nothing here telling us what base this logarithm is. This is actually known as a common logarithm. And in a common logarithm, your base value is equal to 10. So, now that we know that, let's see if we can solve this one. And just changing my form, this becomes 10 to the x is equal to 0.001. And we're kind of in the same dilemma. We have fractional base and a whole number base in problem B. Now we have a whole number base and a decimal base. But it just so happens that 0.001, if I were to change that into a fraction, that's the same thing as me saying 1 over 1,000. The 1 is in the thousandth spot, so divide by 1,000. And then, that's the same thing, base 10-wise, 1,000 is 10 to the third. And here we are again, where I've got a numerator of 1. We can write this as a negative exponent. So now that equals 10 to the negative third. So 10 to the x is equal to 10 to the negative third. That must mean x is equal to negative 3, because once again, bases are the same. So this whole thing equals negative 3 there. And going with 64, 2. So just simply changing my form, 64 to the power of x is equal to 2. That's a big base. Producing a power of 2, how does that work? Well, let's do the same thing we've been doing on the other problems. Can we make 64 become a base 2 number? Yes, we can. It's 2 to the 6. This is 2 to the first. So now with the bases being the same, 2 to the 6x equals 2 to the first means that 6x must equal 1. Therefore, x is equal to 1/6. So when your base number is bigger than the value of the logarithm, in this case 64 was bigger than 2, that means you're going to have a solution that's fractional. All right, so there it is. There's our introduction. We already kind of took a peek at it. We have our common logarithm base 10, and if you don't have a log base shown, it's assumed to be common log, so that's the typical way we display common logs. We don't write base 10 there, we just leave it as log of whatever. Then we have what's known as a natural logarithm. We worked in the previous section with a natural base e. And so a natural base e must produce a logarithm as well. And this is known as what we call a natural logarithm. And here's the relationship. Log base e is equivalent to ln, or natural log. And here is a breakdown just using our conversion factor that we looked at the beginning of this section. So we had a log base. So here was what we had at the beginning. Log base by equaling x when b to the x equals y. Well, now we're just changing our base b's into e values. So now log base ey equals x, which means this now becomes an e instead of a b there. But we just learned a little while ago that log base e is the same thing as ln, so now we just replace log base e with ln. So ln y equals x when e to the x is equal to y. So if you're going to have this as a separate relationship for natural logarithms, then you're going to have that one working side by side with our common or just base b log. So know this relationship. There's your two relationships, base b's and base e's. All right, so what do we do with these natural logarithms? Yeah, they're just a different name because we have a base e and that base base of b is just a special value of 2.7182, irrational decimal there. So when we evaluate these logarithms, well, if we have base 10 logarithms, your calculators can handle base 10 logarithms. If you have other than base 10s, then there are some calculators that have change base options. Others don't. We will learn how to convert non-base 10 logarithms into something that we can plug into the calculator. Natural logarithms, though, we use with our calculator. It works for all of them. So let's work on just evaluating some common logs and some natural logs using our calculator. First, just for the practice, we'll get in the habit of just changing the form so we can see what it looks like, and then we'll actually come up with the answer from our calculator. So for A here, we have a log base 10 of 0.85, and that's going to convert to a 10 to some power is equal to 0.85. And what we were doing before, where we were able to change the bases to become the same thing, that's not possible here. So now what you would have to do, if we hadn't had any discussion on logarithms, you'd have to start guessing and checking what some values of x could be. Or maybe you graph 10 to the x equals y, and then you see for where that graph is equal to 0.85. Well, that's what a logarithm allows us to do. It allows us to actually find out that variable. So if I were to simply take my calculator now and actually find the log of 0.85, because it's a base problem, we would find that the log of 0.85 is about negative 0.0706. Just by putting it into the calculator. And what about the natural log of 22? Well, again, we're changing our form here just for the purpose of practicing that. This is right now natural log of 22. We change that to e to the x is equal to 22. Once again, what power would I raise e to? Again, checking and guessing and checking. If we just plugged it into the calculator, natural log of 22, I would get an approximate answer of 3.091. There we go. So get familiar with your functions on your calculator for natural logarithms and logarithms. See, we're seeing a lot of the things that we've seen in previous chapters. We're making we're reviewing, we're revisiting. This information is spiraling back into our material here. Here we are again with inverse functions. We were working with that, chapter, 5 or something? So inverse functions, again, what that meant was I had two functions and I was able to composite one into the other and then switch the order of that composite, f of g of x, g of f of x. If they both produce an answer of x, then I knew that I had inverses of one another. Now we're going to see graphically in just a second that a log function is the inverse to an exponential function. But here we have some very useful relationships regarding what happens when you're taking the log base b of something to a power, where the bases of the log and the base of this exponent piece of my logarithm are the same thing. If that happens, I just get an x. And we'll take a look at using the change from log form to exponential form, explaining why that's the case. And on the other end of things, what if we started at an exponential form, where now my power is a logarithm? And again, the base of the exponent, the base of the logarithm are the same. I still produce an x. Let's see what's going on here. Let's just take generic log base b, b to the x. And if I were to change the form on this, so out of exponential form, so I'm going to, again, do this. Log base b to the y equaling x. There's my b. This whole thing is my y value, and this is my x value. And this becomes b to the x equal y. Well, now that means I get b to the x equal b to the x. So guess what? X is equal to x. That's what's happening there. All right, let's try that then here. Now, these properties that involve log base b's also work with log base e's. So in A, I'm in exponential form right now. I have an e to the natural log of 9 power. If I were to change that back into log form, this would become natural log. So here, let's put down below this. This is in e to the x equal y form, and I'm going into natural log of x. Natural log of y equal x. So that would mean in changing this form, here's my x, I'd have natural log of y equals the natural log of 9. And here, both of them being natural logs means that y is equal to 9. So this solution, just by, again, using my conversion form from exponential to natural log form, I get that y would equal 9, or my solution would equal 9. When I am taking e to a natural log of any number, my answer will always be just that number. And it's because of this property right here. There we go for that. Log base 327 to the x. All right. How would we rewrite this? Well, that 27 is the same thing as a 3 to the third to the x. So this then becomes log base 3 of 3 to the 3x power. And in this rule, we say when the base of the logarithm and the base of the exponential piece of what I'm taking the log of are the same, that I just am equating this thing to just the power there, in this case 3x. So this whole thing should be 3x. Well, let's use our conversion from log form into exponential form and see how this plays out. So log base 3 to the 3x goes to 3 to some power is equal to 3 to the 3x. This is what I'm looking for, and it's equivalent to 3x, so there's my solution. That was a little weird, x equaling 3x, but just remember that this is just what I am trying to find, and it's in the same position as, same value-wise as 3x. Some books, instead of using y's and x's for their conversion, they use b's and a's. So that you avoid some of that conflict right there. So don't get hung up on the variables. Just understand the positions of log form and exponential form. And then here we have a log base 10, 6.7. So again, just using my inverse relationships, which is a whole lot easier, this solution just becomes 6.7. 10 to the x equals 10 to the 6.7, so x must equal 6.7. And then finally for D, log base 2, 2 to the 4x. This whole thing's just going to become 4x. 2 to some power equals 2 to the 4x, so there's my solution. All right. Let's find the inverse from the equation now. And when we were doing this back in the previous chapter. We switched x and y and we solved for y, so we're going to do that again. We're going to switch x and y, and now we're going to go solve for y. What that means is we're going to be using a logarithm here. So if I had that, 8 to the y power equal 8x, right now that's in my b to the x equal y form. There's my base, there's my exponent, there's my value. This would become log base b, y is equal to, or in this case x is equal to y. So changing my forms, I have log base 8 log base 8 we have log base b, which in this case is the x, the 8 equal log base 8 of x equaling the y here. All right, so become log base b y equal x. If I switch my forms here, going from exponential form into log form, I'd have that. But because my y is becoming an x and my x is becoming a y here, then I change my solution to become log base b, which is 8. My y becomes an x, my x becomes a y. Again, this is where the confusion of variables kind of gets in the way here, the y's and x's. If I were to make that d and s, for example, then maybe it'd be a little easier to see for your y and x values. But again, thinking about the roles that each of those parts play here. All right, what about natural log? Y equals natural log of x minus 4. Right now, this is in natural log form, and we have, go back from the very beginning, log base b of y equals x becomes b to the x equals y. Well, what if my base is an e? That becomes natural log, and that's when e to the x is equal to y. So right now, this problem is in this form. We got to switch our x's and y's. So we do that. X is equal to the natural log of the quantity y minus 4. And then now we're going to solve for y right here. All right. Natural log of y and x. Here's the natural log. Here's our y value. And there's our x value. So this is going to change into e to the x equals y minus 4. Changing it out of logarithmic form into exponential form. And solving for y, getting y by itself, we would get y is equal to e to the x plus 4. And there's your inverse function for this one. Next one, we're back in exponential form. B to the x equal y. And that happened when we had log base y equal to x. So here's our base, there's our x value, there's our y value. But we first have to switch this. Base is still the same, but now our variables switch their roles here. And this now becomes log base 7 of x equals 2y. And then solving for y, we would have to divide by 2. And now we get y is equal to log base 7 of x all divided by 2, and that would be this inverse function. All right. Natural log again. I'm just going to show you the difference in what if we change the variables. We're just going to use a and b, for example. All right, so switching those, we get b. Now, I'm not going to do the a and b thing. That's going to confuse us with the switching of x and y. All right, we're in that form right now. And this is going to become e to the x. After I switch it into exponential, it's equal to y plus 6. And now solving for y, e to the x minus 6. All right, so there's our changing forms, switching our x and y, and then using our changing forms to get to our new function. And again, be careful with the fact that we got x's becoming y is becoming x. Just keep yourself squared away as to which piece you're working with there. Base piece or the value of the log piece. All right, then we get to the graph component of this. We just mentioned a little while ago that the graphs are inverses of one another, so we've been working with the blue graphs, which are our exponentials. And we can see that switching the values of x's and y's here, I create these red graphs, and that is our log function. Like our exponential functions who have critical movements, our log functions also have critical movements, and they would be just switching the x and y values of our table. When we switch our x and y's for an exponential function, remember that our exponential function has horizontal asymptotes. So horizontal asymptotes hanging out right there at y equals 0. Well, when you switch x and y, those asymptotes also have to switch. And now your horizontal asymptotes become vertical. So our graphs for our log functions have vertical asymptotes instead of horizontal asymptotes. Take a look at the critical movements. Now, in terms of, before we get to critical movements, in terms of the domain and range, so exponential functions said all real values for domain. And the range values were dependent on the horizontal asymptote and whether we were above it or below it. Log functions then switch those roles. So the domain of a log function, if my graph is positive b values, I'm going to be a domain that says x's have to be positive only. And the range then becomes my all real number piece. And you can see that in these red graphs here. Either one of them, you can see that in the red graph, all my x values are to the right of x equals 0. And the graphs proceed positive y, negative y, thus able to take care of all the real values for y. So those are our range and domains, just simply switching with our exponentials. And here are our critical movements from our graphs before. Now, I'm just using these 2 points here. Remember, in our generic exponential graphs, we had these movements, -1, 1 over b, 0, 1, and 1b. Well, look what happens here to 0, 1. We switch x and y, and it becomes 1, 0. And 1b switches and becomes b1. So if I wanted to add a previous point, as in a negative movement there, I can do that as well. switching x's and y's here, I would have a right 1 over b value, and this time a down 1. So if I wanted to add that third component to my critical movement tables, that's what I would have. All right, vertical asymptote this time, no longer horizontal asymptote, is dependent on the opposite of our c value there, where before our horizontal asymptote was dependent on our d. Now we're looking at the x coordinate there for our imaginary start point. So everything's just switching. All right. Let's see what happens. A log base 2 of x, what would that look like? Well, let's put our table together and see what happens. So from our previous info, our parent function table would have been a 1 over b, and then a negative 1 movement, and then a 1, 0 movement, and then a b, 1 movement. Well, our b is now a 2. So now I have one half, negative 1, 1, 0, 2, 1. There is no vertical stretch factor going on. With a log function, a vertical stretch factor would be showing up out front of the word log. We don't have that. There's no left and right translations. Again, we'll look at those types of things later. So these then would be my movements for this graph. In terms of my starting point, negative CP, it's 0, 0. And so my vertical asymptote is going to be the opposite of C value. Is going to be this guy. So x equals 0. We can go ahead and put in that vertical asymptote in then. Have a vertical asymptote right there on the y-axis. And now we'll just do our movements. So right 1 half, down 1. So there's going to be a point. Whoops. Right 1 half, down 1 would be somewhere right there. And then right 1, 0. And then right 2, up 1. And just like we did for our exponential graphs, we graphed for shape once we knew what our movements were. We're going to do the same thing for our logs. So we're just going to kind of graph for shape now. And we would have something that looks like that. We've got a base now, so our base is a 1/3. So when we go and do our movements, we have a 1/3 down 1, and a 1, 0, and a D1. Should be a 1 over 1/3. This is really 3. 1 over 1/3 is 3. Vertical asymptote. Again, at x equals 0, so on the y-axis. And we go ahead and graph our points here. We have our, whoops, 3, down 1, and then our 1, 0, and then our 1/3 up 1. Oh. Hang on for a second. All right, sorry about that. So we have, those are our points there. And this graph looks a little different. And the reason it's kind of looking flipped, sort of here, from our other graph above is because our b value is a fractional thing. So b values being fractional for logarithms, going back to our look at the very first graphs here, when we had b's that were larger than 1, my graph would have started on the asymptote and then grown bigger as it moves to the right. And when our b's are less than 1, greater than 0, then we start on our asymptote on a positive y value and then move down into a negative y value as we move right. So it's kind of like looking at a growth and decay, but these are not growth and decay graphs. Those are exponential, not logarithmic here. So our base values determine the shape. All right, and then some more practice problems here, just a couple more of these. Again, if you wanted to freeze and come in and peek later. In these, we have a negative CD of a negative 2, 4. So that's my imaginary starting point. And with our imaginary starting point, we know we have a vertical asymptote at x equal, in this case, negative 2. My base is a 5, so it's bigger than 1. Using my table values, we have our 1 over b, or 1 over 5. Down 1, and then 1, 0, and then 5, 1. Again, no vertical stretch factors going on with this graph. So those would be my movements, but they're going to happen now from negative 2, 4. Vertical asymptote, right there at negative 2. Doing my movements from my starting point, right a fifth, down 1. I'm always going to be approaching and loving that asymptote there, and then right 1, don't move up and down at all. And then let's move right 5 and move up 1. So my graph is looking like so. And then on this one, once again, imaginary start point, vertical asymptote. No vertical stretch factors at all, so a b value of 2. So we have right 1 half, down 1, right 1, 0, right 2, 1. Happening from 1, 2. Got a vertical asymptote in there. There we go. And then graph them. Right 1 half, down 1. And then right 1, 0. And then right 2, 1. There's your graph. So become familiar with those critical movements. Again, remembering to flip everything x and y's with regards to log functions compared to our exponential functions, and you're off and running. Now, in terms of domain and range, we didn't state those for these, but for domain on this graph, for example, we are greater than negative 2, and the range is y equals all reals, as with any log function. On this function here, again, the range is going to always be all reals. Our domain will be dependent on the location of that vertical asymptote. So in this case, my x's have to be greater than 1, because that's where my vertical asymptote is. And y's are all reals one more time. Let's go back to the other graph, just to finish up the domain and the range here. Both of these graphs had vertical asymptotes of y at x equals 0, so therefore I want to be greater than 0 on both of them. They would both have that domain in the range there. There we go. I hope that was helpful.